That exam is not
So welcome today. Any questions about last time material? Any questions about upcoming material? Okay, so last time we talked about sorry, about the filters, the LC oscillator, and then today we are going to move into diodes. Can somebody verify that you can access the notes? Yes, okay, thank you. All right, so I did put other supplemental material on the sections for lecture 16 and 17, so those should be up there. Your homework for up to today will be due on Thursday, and then your quiz will be posted starting Friday morning, and then you'll have till Saturday morning to be able to turn that in. Any questions about upcoming due dates for that, for whatever else is coming up?
Has the homework been released?
Yeah. Yep, it should be on, I think, 17. So it says homework 16 and 17. And again, it will be 2 files, so do make sure that you submit for both of those. All right, any other questions? All right, so something that's kind of, going back to the moon has kind of come up quite a bit. So thinking about going to the moon, one thing that you may need there is batteries or power. So question is how to have power on the moon. So I just am curious to see you guys' thoughts. Like, how could you actually create and have power on the moon? So take a second and just go ahead and put thoughts as far as how to create power on the moon. Based on your own knowledge that you have right now. That's an interesting one. Here, let me get out of these way. I can't get out of the way. There we go. Bicycle generator? You're just gonna seriously just sit there and pedal all day? Is there wind on? Is there wind on? All right, thank you for the chuckles. So yes, don't have power on the moon. All right. All right, great thoughts. Enjoyed those thoughts. So a couple of them that I saw would be feasible is solar. I saw solar would be a feasibility. So solar and nuclear would be another feasible one. And then, yes, they said a generator. Okay, so I did like some of the others. Thank you for the chuckles. So solar, what is the issue with solar? Anybody?
Only works when it's light.
Okay, and did anybody know? How long? It's like 14, it's like long periods of time before you have, I had it written down and now I forgot where I put it. So it's a long period of time, so you have to have light, so it only will generate So it has its limitations, limited to light source. Any thoughts about like nuclear, why that might not work?
Good enough for the military. It's good enough for me.
Okay, go ahead, Vikram.
Proper reactor be really, really heavy.
Okay, so heavy.
One is just not.
Did you have
Uh,
a thought?
with what we're using right now, we would use a lot of water.
Okay, so it would need other resources.
Is this for space-based applications?
Yes.
Yeah. So these have some limitations. The nuclear would actually probably need the resources, so it would be a lot of somebody traveling there to give the resources, and it would deplete resources and then need to be renewed. So that's a very high limitation of that. What's a thought about a generator? Like what might be an issue with a generator?
You still have to power the generator.
It also needs resources. So it also needs something that's going to power it. So, sorry, I'm trying to find where my notes went. I thought I had them on here. Sure. Oh, the material. There we go.
Wouldn't the limited light source be not really applicable to the moon because there's only one side facing the sun, so you always have a right?
It always faces the earth.
What if you're on the other side? Oh, yeah.
So it does have light. There are locations that you could put it that would have some light, but they're very limited. So they're going to be very small periods of time that it would actually absorb enough light to get enough power out of it. So it would be limiting. So a lunar night lasts 14 days. I knew I'd written it down somewhere. So it's a long period of time before it would actually have some period of time of light. So that's very limiting. Yeah. So lunar night is 14 days, 14 of our days. So, so one thing about any of these three, so say, yeah, we get this to work. Anybody have ever used like solar or wind or anything else and then all of a sudden it doesn't work? So you definitely want a backup system for any of these because they are not quite as reliable as what we have now, which is very reliable most of the time. And even with our very reliable system, there are still blackouts, there are still other things that happen, even with our very nice reliable. So we would want a backup system. So this is what a lot of places like hospitals that are like, that's scary if we run out of power, so they have all of these backup systems. So very common to have a backup system, which would again want to be something to consider. So whatever power supply we decide to kind of create, that is going to go into, you know, whatever equipment we have up there. Say we want to actually create the nuclear power thing up there, and it's going to dig its own area and everything. It's going to need to have a lot of equipment that's going to act as a load to it. So on this, if we put up a backup, so I'm going to put my backup. So say we have a backup power or a backup battery. And how do we add this backup battery into the system? So can we just do this? No, why?
Don't want the backup draining when the main power supply is working. You want it to kick in if the power supply gets cut off.
Okay, so no, don't do this. So what if we have two batteries and we put them in parallel to each other? Not good, right? Don't ever do that. It's gonna be like, nope, this is not gonna happen. Spark, either kill one of the other. Because they are, even though they might be similar, they're not exactly the same. And so remember, you have to have, at one node, you have to have the same voltage as at that same node. So it's feasibly not able to happen. So if something happens, whether one will overpower the other and basically drain it or something else. So you need something kind of in between those. So what would be ideal is maybe if we had some kind of system that actually kind of did its own little loop and was able to kind of charge both systems. Oh, this was just kind of ugly, but some system here that kind of helps to kind of like, okay, if this battery is draining, then I want to actually recharge it with something else. So it uses that backup to charge it. And then if the backup isn't, then it will kind of go back and forth and oscillate it together. So that would be like ideal if the primary power could kind of keep the other battery charged. Oh, that was kind of an ugly drawing, but there is a component that we can use called these diodes. So the nice thing about the diodes is that it can only allow current to flow in one direction. And so this kind of a system would then allow for a backup, which would be here, battery backup. But it's buffered by the power supply, so they're not going to drain each other. And these diodes are really nice because they offer that protection. And so this is one of their uses, is to use it as a battery protector. So it will only let current flow out of it into the equipment. It doesn't let current flow into itself, and so it won't blow up. So a very good, useful thing. So this element here is called the diode. So diode. So the diode has two sides. It has a positive side and a negative side. And the negative is easy to remember because it's on the side with the line. So it looks like a negative. So that is how you remember what side is plus and which side is minus, is this nice. The arrow side is your negative side, or not the arrow side. The line side is going to be your negative side. So we haven't really talked about semiconductors or materials. So conductors, anyone know if I put a current on a conductor, what happens? Anybody know?
Flows through the conductor.
Correct. So it passes current really easily. So it's easy. An insulator. If I put current on an insulator, what happens? So it's hard to pass. So semiconductors is this nice material in between where we do something called doping, and we can dope this material. And by doping it, we can change the charge of a material. So silicon is a very widely used one. We actually we'll dope it with either another chemical that will add in a lot of electrons. And so because they have extra electrons in their orbital, I can't think of the name of that, around their orbit of around the atom, they have that negative charge, so you get a negative extra overall charge in the material of negative. And then you can dope it with another chemical that is missing extra electrons, and so it has lots of holes around its valence shell. That's what I was looking for, the valence shell around the atom, and so it will actually give you an overall charge of a positive. And so what we do is we combine these two. And so these are silicon-based materials that this is a model of. And the P stands for the positive charge, P for positive. So overall positive charge. And the N stands for negative, so an overall negative charge. So this is called an N-type material, and this is called a P-type material. And anybody remember or know, if you haven't taken chemistry, if I have two charges that are opposite each other and I just put them together, anybody know? Do you know what happens? Okay, you create a field because there's a difference in the polarities. Anything else?
It becomes neutral.
Okay, so the boundary between where they are wants to become a neutral area. And so you get some of the positive charges go over, and then some of the negative will move over, and then the holes kind of move also. So you get a barrier, like a little layer in there that's like, oh, okay, I'm creating a neutral balance between these two because they're opposite. So they do actually, do attract to each other. What happens if we put a charge on there? So if we have a battery on there, and we put plus side to negative side, and again, like the negative on let me draw it again. So on the actual symbol itself, the N-type is where the negative is. What I was saying, this is the negative side, this is the positive. So this is the P side, and this side is the N side. So N is still negative. So this has a plus here and a negative over here. Plus there and a negative there. Okay, so kind of visualizing this. So now we put a battery on this. And when we put a battery, this is going to look like this, plus and minus, which is matching the polarities on this also. So what happens here is the electrons have, how do I say this? So with adding on extra charges, your opposites are going to attract. And so there's going to be, the electrons are going to go fill the holes on the P side. And so your electrons actually move in this direction. And if you remember from physics, our conventional current is actually flowing in the opposite way the electrons are moving. So that means that the electrons flow in this direction, and our current is going to flow in this direction. Or we define our current flow as opposite that. So this is then going to have a current movement from the negative to positive. So it flows in this way. So our current moves through the diode in that way, meaning the electrons are moving to the left. So what happens if we put opposite, and now we've put the plus on this side and the negative on the opposite side. So when I draw this, I have more positive on the side that wants the negative, and so it's opposite, is that the electrons are going to actually be attracted to, as you can see over here on this side, so they're going to move towards the battery, and the holes are going to want to have, they're going to be attracted to the negative side of that battery, and you get this big layer here called the depletion region, where all of those charges have moved away from that boundary. And it creates this big barrier. And so there is no current flow in this case. So it basically shuts off and there can be no current flow. So the symbols, as I showed you already, which side is the negative and which side is the positive on this one? The which one?
Cathode.
Okay, so that will be your negative. And then the packaging itself has this little line on it. That indicates that that's the negative side. The other type of diode that you may have seen or you're going to see is the LED. So this is a light emitting diode. And it actually lights up, emitting diode. And the polarity again is the same. The line means the negative. And on this one, there's going to be a little flat region. And that's how you know physically where the negative part of it is. So those are on the physical devices where you're looking for to say that's the negative side of this diode. So when it is on, meaning that I have more positive voltage on the left, on the anode side than the cathode, my current will flow through it. Here, when the current flows, it actually emits off light that you visually can see. So once I've reached enough voltage across it, it will actually put out light on it. So little red light or other color. Okay, this is a photodiode. And a photodiode works in that if I have enough light, it will actually pass the current. And the interesting thing about it is it actually passes the current in the reverse direction. This is working, it's called avalanche breakdown. So it works a little bit differently than the other one. Okay. So current flows when you have enough light. But do note that it flows in the reverse direction than the normal diodes. All right, questions about the diode so far? Yes.
On that last one, that means the negative would be on the other side, right? Or is the negative still where the line is?
So it's still where the line is. So it still is considered positive to negative. But this doesn't turn on based on voltage. Instead, it turns on based on the light intensity. So I should say it can still work in like a normal diode. Like it can pass current going in that direction, but it's usually not used that way. So usually it's used with the current flowing in the other way once I get a specific amount of light intensity on it. And then that current actually has a nonlinear form to it. So based on that, I can tell, like, it usually can determine like differences in light intensities. Right, any other questions? Yes?
What's the distinction between a photodiode and a photoresistor?
So a photodiode also will stop, it will limit the current flow. Like it, as I said, it will have a current flow in one direction, but it really only operates in the opposite direction, where a resistor, it can go either way. So it just depends on what voltage you put up to the diode, or not the diode, the resistor, on how much current will flow through it. This one will pass it and is more like a switch. So it's usually more like, oh, this is on or off. Where a photoresistor also will change its resistance value as the light changes. And it does it, it's more linear. So it will give you a more linear response. As I change the light, the response will be more linear, where this one will be nonlinear, meaning a graph of a curve. It's actually in the opposite direction, so it goes this way. So it will, oh, that's a really bad graph, but it basically, I can't draw. It will be nonlinear. This one's easier to draw. So instead of a linear line, it will be a exponential. It will follow that form. All right, any other questions? All right, so this is, so this section here is where it usually works when it's that backwards reverse current. It's called avalanche breakdown. But we usually work with the LED, which is the light emitting one, and the silicone diode is right when you are 0 and above. But it takes some voltage to be able to overcome, remember, the barrier between the two. So that's called the VOD, will be the turn on voltage, diode on voltage. And so depending on the type of material that was used, it's usually 0.6 to 0.8 for silicone. So this is the VDO, or diode on voltage. Schottky is a little bit lower voltages, so 0.4, and then with germanium is even lower. So for all diodes, they take some energy or some voltage to even turn on. So you can see here there's no current until we kind of reach that threshold, and then it's almost like a straight line, but it's still nonlinear. So we usually approximate this as, depending on what externally is connected to it, we can have different values of current. But they're the ones, so that's the other thing, like the difference between a photoresistor and a photodiode is that it takes another resistor on the outside external circuitry of this to be able to determine what that current flow actually is. The diode internally doesn't do that like the photoresistor does. Does that make sense? So it's like more of a switch, on or off is an easier way to think of a diode. So seeing this, we know we have to overcome this voltage in order to turn it on. So we model it as either a diode is on or off. When it's on, it will pass current. So current will be greater than 0 when it's on. And when it's off, your current is 0. In order for this to happen, you need at least the voltage across it, which I'm calling VD, which is going to be that voltage between the plus and the minus. VD needs to be at least equal or greater to the turn on voltage. So we're most of the time going to use silicon, and as I said, it's usually 0.6 to 0.8. So usually if for hand calculations, I like to use just 0.7 volts. So if it's off, that means that VD is less than 0.7 volts. All right, so one thing, like what happens if I just put a diode directly across a battery? So this is going to give me a large amount of current flow because it's almost like when it's on, it's another voltage source, right? So it's like there's no resistance at all. So a lot of current will flow because it will be like a wire. What happened to the wire when we hooked up a wire directly, or you saw that video that hooked up the wire directly to the other side of the battery? You guys remember that video? What happened?
It's hot.
It gets really hot, yes. Hot. Ouch. So it can actually melt it. So we don't want to do that. This is called thermal runaway, where it just will melt. And probably destroy your diode. So we need to have a resistor, at least one in there. And again, depending on that value, you want to make sure that it's not too low, because if it's too low, it's also going to melt. So, so just a side note to make sure you don't hook up the photodiode like you would a photoresistor. Okay, so let's look at actually calculating a circuit with the diode in there. So what we're going to do is you first make an assumption. So you make an assumption. There's only two choices, on or off, for the diode. If on, you're going to redraw the circuit with a voltage source instead of the diode, equal to its on voltage, and if it's not given, then you just make an assumption that it's 0.7 volts. And then you analyze the circuit, and then you need to check that your assumption was correct. The checks for a on diode is if your current is greater than 0. So that's what your check is. If it's off, you have to check that the voltage across the diode is less than 0.7. All right, so redrawing this. Oops. I keep the polarity the same. So the polarity was a plus on the top and a minus on the bottom. So the polarity stays the same. So make sure you know that, same polarity used. And then I use that 0.7. And then I can solve this, so I know ID is flowing in this direction, and this is plus to minus. So taking a loop, I get plus here, minus there, and I have plus 4 minus ID times 1K equals 0. So I get ID is 4 milliamps. Sorry, I assumed it was on too. Oh, whoops, I forgot my 0.7, sorry. I was gonna say that's not the right answer. So minus ID 1K minus 0.7 equals 0. And then this is ID is 4 minus 0.7 over 1K, so 3.3 milli. All right, so I made an assumption on, I replaced the diode with a battery, 0.7 volts. I then solved the circuit, and then I needed to check. What is my check for this one? Correct. And is it? So then we're good. So like that assumption was correct. So if I had found that the current was negative, I would be like, oh, I need to reassume that this is now net off and resolve the circuit. If I assumed it was off and I solved the circuit and found like VDO was actually greater than 0.7, those would not match. So then I would say like, okay, no, my next assumption is that it's going to be on. If you work with more than one diode in the circuit, you have to be careful that every time you make a new assumption, you reanalyze the whole circuit again, because the circuit will be a different circuit with an on and off. All right, questions about the steps on how to solve for circuits that have diodes in them? You guys? Okay, so this is a data sheet for the one that you're going to work with in the lab. So this is the 4002. And the 4002, where did it go? On here, you're going to see that, you can really see it there. The output current, I naught, is going to be 1 amp. So on this, you want to also check that you're not going over 1 amp. So say you have a design and I had a really small resistor there, which meant my current would be a lot higher. So if I put 10 in there instead, that's going to be 33 milliamps. Is that still okay? So this 1 amp is going to be kind of your limit. So yeah, it'd still be okay. But you do want to be careful, because if you put, what if instead of 4 volts, I had 40 volts? Then I might reach that limit. So you want to be careful with that, to note, like, I don't want to go above that 1 amp. What happens if I go above that? Any thoughts?
Melts.
It's going to melt. Yeah. Or it will also start getting hot. So if you start smelling weird things in the lab, be like, okay, somebody check really quick. Turn off your power. Make sure you haven't put 40 volts instead of 4 volts on there. All right. All right. Go ahead and work on this one. Find my... Oh. Okay, make an assumption for the diode, and then try to solve for VD and ID. And note that VD is referring to the voltage plus on the bottom and minus on the top of it. And then go ahead and put in what your VD and ID is. If it's not good.
Okay.
I didn't show that part of the data sheet. So on a data sheet, there'll be an on voltage for a specific current. So typically you can use that.
So if you look at the max current,
So
just
it
assume
will
one
be,
endpoint.
it will be on a data sheet, and it will depend on how it's been calculated. The VDO, the on voltage is usually, as I said, usually between 5 and 6. That one's easier to figure out. Can you just make it? 0.7. The reason the current is harder is that it depends on how it's doped. If you heavily dope it, you will have a lot of current. So that's why that one is the what? So you need to know more information. So you have to know so there's equations that you can look up for so you have to understand drift and diffusion a little bit more. And then you, based on those, you can actually calculate a diffusion current and then say like, okay, based on that, this would be my diffusion. Usually it's so small we can hold it by hand.
So on the sheet, it was like paper.
Yes. And some of them may run out of go. And it is based on the diffusion. The doping that was done with it.
Oh, I added.
No wonder why. No wonder.
Okay. So try to see what it is. Oh, it's an otter. I tell you, you guys are very creative figuring out how to. Anyway, great. Okay, so -4 and 0. I like the zeros. So how do you say, is VD 4 or -4? So that looks to be kind of more of the question. So with a 0, that would be an assumption that it's off. This is 2K. I used the wrong one. That's okay. Okay, so with it off, I forgot to say with it off, it's just going to be open. So when it's on, it's the voltage source, and when it's off, it's open. So with open, that makes it easy because we do know, like, I would be 0, either direction. And then the plus is on the top for the 4 volts, and the plus is on the bottom for this one. So as I take a loop around, This is plus, so my loop would be plus 4 plus VD equals 0. So VD would be considered as minus 4 volts. So it was correct to say VD is minus 4 and ID is 0. And then what's the check for off? Correct. The voltage has to be below 0.7, is it? So minus 4 is less than 0.7, so that is correct. So our assumption of it being off is correct. So again, if I had solved this and put in the voltage source of 0.7, I would have to put the current flow going from here to here to match the polarity of the diode. And so that direction would be what I would solve for ID. And then you should find that ID would be negative. Okay, try this one. So calculate VD and ID for this one. What is the polarity on the 12 volt? What on the battery? Anybody? Which side's positive and negative? Thank you. So positive's on the top. And on the 4 volt, positive's going to be on the top too. Okay. Just a hint. There's a good consensus here. So these are correct answers. Good job. So current has to flow, again, the direction of the plus to minus on this. And we're going to assume on. Again, you could assume off, but one way to kind of make educated guesses is to ignore all the resistors and then look at the voltages on each side. So if you look on the positive side, you're like, oh, that's connected to a 12-volt battery. And then on the negative side, it's like 4-volt battery, so that's going to be less than the positive side. So most likely, I'm going to make my first guess of on. So that's kind of how you want to look at it when you look at what am I going to guess first. Doesn't always work, but it's just a way to say that might be my first guess. So assume it's on, so I'm going to redraw with a 0.7 volts where the diode is, and I keep the same, again, polarity. So with that, the plus is on the left, and my current is going to flow in this direction. So I call that ID. So that means it's going to flow in this direction. And so I have a plus, minus, minus, minus. I forgot to write 0.7. So plus 12 minus 0.7 minus 820 times ID minus 4. And solve that for ID. And that gives me the 8.9 milliamps. I then check it, and the check when it's on is ID greater than 0, and it is. And so the VD is just the 0.7, since that's what I chose. So VD will be 0.7. Don't need to check. All right, questions? You guys feeling comfortable with this? Okay, so you get to do more of these for the homework. Yes?
Is the voltage drop over a diode just based off the material that it's made out of?
Uh-huh.
Okay, all right. Sweet.
Yeah, so it's that junction and how much voltage do I need to overcome that small little barrier.
Right, okay.
So that's what it is. So yeah, it's based on the materials. Okay, so I'm going to go to an application. So motors might be something you guys see a lot. So on a motor, it actually, when you turn on a motor, it acts like a inductor and resistor. So you can model a motor. So can model, put model. So you replace with an inductor and a resistor, so an L and an R. So if I had just, say I connect this to a battery, and I have a switch in it, this would be how I could kind of model the motor. All right, so this looks like a circuit you guys have seen, right? LR circuit with a switch. And so when I don't have a motor connected to power, and then when I connect it, that's when the switch would close. So I could actually write the equation for this by finding the initial time would be, or the initial current would be 0, because there will be not connected. And then when I connect it, I can find that exponential curve to find the voltages and the currents in there. So you guys have learned how to solve this, and now you understand that that can actually be what models a motor. So on this, when you have a switch, what actually happens, like when you open it after you've kind of charged it up. So after it's kind of been charged and then you open it up, air acts as, you know, a really, really, really large resistance. And so you get this kind of what's called a gap resistor. And in this case where you have, you know, the plus and the minus, and then this has been charged up to give you a drop still of a plus to minus. Right as you open it up, the current still is flowing. So no current will flow right when you open it up. But then what happens is, you remember with the L and the C together, even though there's not current flow, it's going to still try to force that current to flow in that direction. So it's going to create a flow of current. And in this case, we call this a flyback current flow. And as that's going, it changes the polarity here because it's forced that current to still flow in that same direction. And so you get a spike. So you get this spike effect in it, which is not what you want. And it's called an inductive spike. And so one way to remove this is to add a diode, which is going to limit it. Once it's reached that threshold, it will turn it off, so you can't actually get that flow going in this flyback current. So we remove the inductive spike by adding on this diode. Oops, I can draw. So as it switches, we orient the diode so that it is in the opposite way of that power source. And so it won't turn the diode on until it starts to see that the inductor start trying to force the current, which will change its own polarity of voltage. Once it does that, then the diode turns on, and instead of having the flyback current, it will cut it off and flow through the diode instead. So it will remove that spike on the bottom down there, and then it only will have the drop across it as much as the diode is. So some of these inductive spikes, especially when you get large equipment, like goes up to, one guy measured it, let's see, what did he measure? It was like 100 amps, I think it spiked to. So, you know, not good for a system to have such a large spike in current. And so this was one way of mitigating that, is to use this diode. So this is called a flyback diode. So this is one application that's also very useful that you guys may see as mechanical engineers. All right, LED. So we've only talked right now up to silicone diodes. So an LED takes more voltage across it to actually turn it on. So instead of that 0.7 volts that we have with silicone, this is going to be 2 volts. So it needs about 2 volts in order to have it turn on. Some of them are even as high as 3 to 4 volts. So depending on the color, you'll get some. I think green might be one that's like 3 volts, 3.3 volts, I think it needs to even turn it on. So you want to look at a data sheet, you know, specifically for if you're looking for a specific color too. Like how much do I need as far as a voltage minimum before this would turn on. So same technique will be used. Go ahead and try and find Let's see. Oh, one other thing too is that for LEDs you need a minimum current flow. So for LEDs you need about 10 to 30 milliamps of current to be able to light up. So they have kind of two requirements that need to be met in order to light up. So when you replace this one, if you assume on and replace it, you need to use a 2 volt instead of a 0.7 volts. So go ahead and try to find what your ID will be here and whether this will be on or off.
Isn't that current will still flow through it, but it won't light up, or does it? Okay,
So if it will still turn on as long as you have the 2 volts across it,
but it won't light up.
but it won't light up. Yeah.
Okay.
So say I have 9 milliamps, and I have enough to have 2 volts across
So
it.
current will flow, but it just won't be on.
Yeah, it will flow and it will still meet the conditions of like, oh, it's still on. It just won't light up. It won't be bright enough to light up.
Like it won't be bright enough to light up visibly or
Correct.
at all? Okay.
Yeah, I mean, it will still, be emitting some
Some small amount of light.
small amount, but not visible.
Okay.
It will be super dim.
Okay.
It wouldn't be a current divider because that's not a resistance. And then once you find, so you would need to find I1. So hint, not a current divider. So like looking at this, if you ignore the resistors, you're kind of looking at 5 volts being at the top of it.
Okay.
And then kind of the reference to the ground. And so that plus and minus matches up with 5 volts. So we would say. So good job. Looks like you guys that did answer are on the right track. So it doesn't light up, but it does turn on. So redrawing it, seeing that, like, ignoring those resistors again. So I have kind of on the top 5 volts, and then on the bottom would be more of a reference location. So I could assume maybe first that it's on. So assuming on, and then replacing it. In this case, I need to replace it with a source of 2 volts because it's an LED. So this is going to need 2 volts here, and then the current still flows from the plus to the minus. And as I said in the hint, you can't use a current divider here because it's a voltage source, not a resistor. So the only way you can solve this is through voltage loops, or you can use node voltage if you learned that. So in order to know what the current ID is, I'm going to have to do a current summation at that blue node. So I1 goes in, and I2 and ID go out, so I could describe it as this. Or I could say I1 is equal to minus I2 minus ID. So ID is going to be I1 minus I2. And then I2, I know the voltage across it because of the 2 volts, so I can use Ohm's law there and say that I2 is 2 over 1K for 2 milli. And then on I1, I can either notice that the plus side has 5 volts on it, and the negative side has 2 volts on it, so I can say that voltage difference is 5 minus 2 over 1K for the current there, which is kind of what you do for node voltage. Or if I don't see that, I can just do a loop and do a plus minus minus. So plus 5 minus I1 R1, which is 1K, minus 2 equals 0, and solve for I1, 5 minus 2 over 1K for 3 milli. Or, as I said, I can say the plus side, which is 5 minus 2, the negative side over 1K, which is the same. So then plugging it back into this equation, I get ID is 3 milli minus 2 milli for 1 milli. And then my check is that ID is greater than 0, so it is on. It just is not, won't light up. Oops. All right, any questions about these? Okay, you guys have enough to be able to do the homework for Thursday. So Friday quiz will be on kind of the LC and diodes. See you guys on Thursday.